Hello and welcome to the Our Connected World podcast brought to you by TE Connectivity. I'm your host, Michelle Dawn Mooney, and today we're talking about the evolution of eVTOL technologies. It will be a two-parter because we have so much information, we will not be able to get it into just one episode. Every day in the news, we are seeing news stories about the electrification of aerospace, specifically on electric conventional takeoff and landing vehicles known as eCTOLs, and electrical vertical takeoff and landing vehicles known as eVTOLs. Today, there are new companies jumping into this bustling industry as imaginative prototypes are getting tested and air transport companies continue to announce plans to introduce electric aircraft into their fleets. I have two great guests to bring on today for this conversation. Matt Macalonis is an engineering fellow at TE Connectivity and is the director of advanced systems and architecture for the Aerospace and Defense Business Unit. He is an experienced engineering leader with more than 29 years supporting customers with connectivity solutions for TE Connectivity. Matt is a trusted subject matter expert for TE's aerospace business, focusing on VPX components, high-speed embedded computing, among others. And Matt hit a patent milestone of 50 issued U.S. patents in connectivity-related technology. He holds a black belt certification in lean design for Six Sigma. And Martin Cullen is a senior business development manager at TE Connectivity, serving as the global eVTOL leader for the aerospace business. Martin is responsible for defining TE's strategy for the emerging aerospace markets. Martin has 23 years of experience in the aerospace industry and works closely with TE's engineers, product managers, and commercial team on electric and fiber optic systems and components. Thank you, Matt, for being here today. We're excited to get into this conversation, so appreciate you being here.
Thanks, Michelle. Great to be here.
And Martin, thank you for being with us as well. Excited to get into this conversation with you. So appreciate your time.
Yeah, great. Looking forward to a fantastic conversation.
So we're talking about the evolution of eVTOL technologies. And I just want to start off with this. How are electric aircraft architectures similar to and then different from those in electric cars and electric trucks?
Yeah, so what we're seeing in the past couple of years since eVTOL has really come to the forefront of advancing aerospace technology is a lot of the know-how it's come across from experience with electric vehicles, electric cars, electric trucks, as you say. So even down to the employees, we're seeing are coming from that market, that industry, and knowing what they know and trying to get to the market as quick as possible. They really have repurposed a lot of the technology, a lot of the architectures that they are used to designing, manufacturing, and us as consumers using are these electric cars. So typically, technology-wise, performance-wise, we're seeing similar kind of battery packs running at a similar kind of voltages, 400 in the very kind of base level for electric vehicles, up to 800. That's where the aerospace electric aircraft tend to be operating right now. Is around the 800 volt system, really employing kind of the very simple architecture of a battery, a power distribution unit, and inverters and motors are being carried across and ideally optimized for the specific aerospace architecture into what we will see with these eVTOL and eCTOL aircraft. But obviously, there's a lot more of the motors involved, and these aircraft are a lot more power hungry than electric vehicles. So you see a lot more battery packs. You see a lot more motors, and ultimately a lot more redundancy. Because obviously these cars, when you drive a car down the street, you have an issue, you run out of charge, you kind of pull over to the side of the road and you get rescued. But when you're flying a few thousand feet up in the air, you don't really have that luxury. So we have to bump it up in terms of safety, in terms of robustness. So you tend to have greater redundancy of systems. You have more battery packs powering different configurations of motors. You tend to see aerospace grade components in the safety critical architectures to ensure that these vehicles are safe to fly. And so, yeah, so it's been quite a learning curve, particularly for those in the startup organizations to kind of come up to the aerospace way of working with the agencies and the authorities and regulatory bodies for aerospace. So yeah, it's a really interesting time of how we're kind of melding aerospace and automotive technology. So there's a lot of similarity, but at the same time, it's quite a bit different because of the standards and the safety aspect.
When you think about electric cars, electric trucks, and compare them with electric aircraft, we're now defining this in a three-dimensional space versus a two-dimensional space. So when you only have to think about driving on the road and your your steering wheel versus lift and navigating in that between buildings and power lines and stuff like that. So the types of systems that are required to fly in that vertical type of space require additional systems and especially sensors on the motors and propellers and things like that, which you probably don't have that level of sophistication in the car driving vehicle. So what does that mean for, again, safety is even more critical.
So clearly there are some differences. And, I believe it was you, Martin, you talked about the difference between a car running out of, energy there and having a plane that's quite higher up and a lot different there. So tell me, how are eVTOL architectures different from those in traditional aircraft?
Yeah, great question. So when we think about eVTOL architectures and think about the vertical aspect of it and compare that with traditional aircrafts, so aircraft will have a generator creating electricity on an airplane. So if you think about just flying commercially, you have every comfort available to you. You're entertained, and all that's running on electric. You're communicating, the avionics systems. That's all based on some batteries, but on the engine you have a generator. So the generator's typically creating often a three-phase power that comes off of that AC power. And when we deal with eVTOL, especially the pure electric aspects of those, you have many, many batteries that are responsible for the takeoff, so creating that lift feature, and then also at cruise, and then also any other avionic system or comfort system on the aircraft. So what we're seeing is, the batteries create an issue in that when you fly batteries around, they're not getting any lighter. When you fly traditional conventional aircraft around, they are burning fuel, consuming fuel, and also creating more efficiency as you fly. So one of the main challenges with the electrical architecture is to design things efficiently, especially with heavy batteries, and where you place them to enable optimum flying characteristics. And what we're also seeing with the architectures is the power required to get lift is very, very high. You're talking megawatts of power. And power is a function of how much amperage and voltage you can put through your cables and connectors. And so if weight is already an issue and current is typically related to how big the wires are, you don't want your wires to physically get bigger because they A, won't fit, but B, they're very, very heavy. So the other lever you have is voltage. And when you create higher voltage, that creates a, relatively speaking, a very dangerous situation with high voltage. Think about lightning bolts and the amounts of voltages in those forces of energy. And with the voltages we're looking at, they're pushing around 1,000 volts. So that's a very, very high voltage. So the insulation materials have to be extremely robust. If you have any kinds of scrapes on a cable or something that create a failure mode with high voltage, is very, very dangerous. So in these architectures, we have to consider safety especially. The other part is how do we charge and or how do you get that energy? So the charging systems is something that has to be thought through in the infrastructure you're flying around. So whether it's an airport or let's just say you land on a building, you need to have the ability to get charging, and charging, I would say, is a key piece of the infrastructure that we still have to develop with eVTOL.
Right now, there are many iterations of eVTOLs. Why? What are key similarities and differences in the technical architectures emerging across the industry?
So this is a great question. I mean, this is a fantastic question for future MBA business students. They're going to look at this market for decades to come to kind of really talk about what's happening here. So, if this goes right back to the early days of the automotive industry, the 1900s and 1910s, when you had hundreds of motor car companies, motorcycle companies out there, and names that are kind of now consigned to the history books, but sometimes live on in different generations. So why are things happening the way they are? Well, essentially, this market is completely new. We haven't seen anything like this before. One thing you shouldn't think about eVTOL is that it's electric helicopters. It really isn't. Now, what we're seeing is perhaps a 3 to 5 time reduction in operating costs. And if you remove the pilot and we go fully autonomous, we should start seeing price points for consumers that are very similar to taking a taxi across the city, or they're taking a train fare from one city to another. And it really is down to how this market is kind of growing. So it's finding its feet. And right now we're in this kind of first generation of market leaders where, again, a lot of them are startups, so they are working to their investor timeframe demands. The business model itself, how is the public going to access these aircraft? What is that business model? How is it going to be validated? What is the mission profile? I mean, people are expecting. Uber Elevate did a great job many years ago to kind of really kick off this industry. It kind of it showed a future potential out there of what the public could be doing with urban air mobility and electric aviation, electric aerospace. So what we're kind of seeing is a bit of it's kind of Darwinism almost, as a lot of these kind of use cases get understood. The customer base, whether you're looking at doing a freight or cargo, whether you're looking at doing a paracivil type application of security or fire service or emergency service operations, or whether you're doing passenger commuting or transfer, how you do that in last minute, last mile kind of delivery services, or middle distance or longer distance, and whether you do that regional, or whether you do that across cities or across lakes or across mountainous regions, all that kind of plays into shaping what these aircraft are, how long they're going to fly, how far they're going to fly, how much payload, whether it's passengers or cargo, kind of comes down to many niche markets. So that's one aspect. That's just the market aspect. And then we're kind of looking at the technology. So I kind of mentioned earlier, a lot of this technology is kind of transferred, particularly batteries, from automotive into the aerospace domain. So as we grow that technology, as we learn more and more and make these batteries more efficient, the chemistry more efficient, the packaging more efficient, the connectivity more efficient, not just in the batteries, but in the high voltage system, we start designing specific eVTOL optimized components, kind of like what we are doing. Now you can see efficiencies there in weight, you see efficiencies in assembly, you see efficiencies in packaging that these aircraft demanding. You're going to see this gradual evolution from this first generation of trying to find out how it's going to be used and using current technology, through to, as the industry matures, as the market matures, then start looking at how can you make the architecture efficient? How can you go up in higher voltages? How can you address the market more as, essentially start creating a demand for the market? Because this is so new. You're going to open up different mobility options for people. You're going to be able to connect cities today or in the very near future that take just half an hour to get across, where in a road system or rail system takes many, many hours. Norway comes to mind in particular, for example. So the reason why this is all really taken kind of many iterations is there's a lot of learning to be done, not just in technology, but in the market application and who the customer is. So super exciting, and this will continue for many years to come.
It definitely is. And you talked about the growth, and it's so new and it's rapidly changing, hard to kind of keep up with that demand you spoke of. But given that this is a very early stage of development and that the technologies are undergoing constant iteration, as you mentioned, how reliable are the technological architectures in this current iteration of electrical aircraft? And more particularly, what is required to ensure these technical systems operate with the durability required of flight over time?
Yeah, another really good question. And this is why, at least at TE, our approach is to think about our aerospace products and components that have decades of proven industry performance and redeploying those types of products and materials. There's something in aerospace called the TRL level, or technology readiness level. And that's very important to understand when a new component is proposed to be used. For example, if it's used in an electric car, what's the difference in the environment when you use it in an aerospace environment, and what's the expectation of reliability of those components? So as we think about the different architectures and the iterations of aircraft, there is a lot of learning going on. And when something fails, it makes big news. So you don't want to have something, if it fails, you want it to fail in perhaps a test environment. So when we think about even the structures and traditional aircraft, the propellers are usually mounted on the fuselage or very close to the fuselage. And some of the new designs that we're seeing, the propellers are mounted further out on the wings, and they're not just mounted further, they have articulating motions on them. And so we're seeing a lot of different things as they do tests and flight. Our cables have to connect to electric motors, means they have to have a different level of flex endurance. Typically in a traditional aircraft, you're not going to see that type of flexing. The routability in tight spaces means we're looking at new geometries for cable, and all these have to be validated and tested. So over time, we do have a long pedigree and a long history, very good pedigree, a long history of the types of materials that we've been using in our connectivity products, our power switching products, and also our wire and cable products. So we have many tests that we already do that are industry standardized, that the industry has helped us to ensure the durability of flight over time. And these are things like, how does it handle the temperature ranges, whether it's hot or cold environments? How does it handle the typical chemicals that an aircraft will be exposed to? For example, any kind of fluids, which typically aren't going to be around an electric aircraft, but they will be around typical aerospace environments. There's other things like de-icing if it has to fly in a cold environment. So those are just a few of the aspects. There's a lot of testing done around salt environments. So salt can be a catalyst for a lot of things, including corrosion and things like arc tracking on cables. So we have to be very aware of these things as we deal with the higher voltage and doing electric flight.
So Matt, a follow-up to that, for eVTOL engineers, what would you say are some technical concerns that are top of mind when it comes to developing I'm curious to hear your answer on a few things, but let's start off with battery connection systems. Can power be transmitted efficiently without compromising weight and while minimizing cost?
Yeah, so battery is a really interesting area because, as you know, with a lot of the devices you use, the battery energy quality at a full charge is not the same as the energy quality at a very, very low amount of charge. And so if you think about flying and you think about when that low battery light comes on and you're flying and do I have enough time to land? That will make, passengers very, very nervous, I would think. And so the quality of the connections are very important, especially in vibration and making sure that every connection, literally every connection counts as you think about this core energy supply in flight. And so when we design our connectors, we want to have efficient material usage in there. And the function of current carrying capability is a function of the cross section of the material and the conductivity of the material. And also the shape matters as well with heat transfer. So we spend a lot of time in designing these optimally to make sure you get the less loss of energy connecting to the battery.
What about electric motor connectivity? What power and voltage requirements must be addressed to ensure reliable daily operations?
Yeah, so one of the, I would say, new aspects of electrical motor connectivity, it depends on where the motor is mounted and if it has to do things like articulating during flight. So typically it would be mounted in a position to enable the vertical part, and then it would articulate so it can do the translation part of the flight. And so when we talk about our cables and how we rate them and thinking there might be thousands of flexes during one flight, that now becomes probably a maintenance issue. And so enabling quick maintenance on aircraft is important, and also being able to do inspections and understand the life of any kind of component in terms of what's the span of maintenance period for it. So these are some of the things as we deal with high voltage, and when high power and high voltage, as I mentioned before, when it fails very dramatically. It's, lightning bolts that could, arc to different surfaces. So we have to be very, very, very careful as we do these designs and test them and make sure that the electrical motors, some of the other aspects we do in commercial aerospace is design for what if it fails. For example, if a motor would fall off, what happens to the cable? Does it rip out of the airplane? And we make some special terminals that are designed to even break, so it doesn't pull the cable through. So there's a lot of very unique things that we can offer for electrical motor connectivity.
With regard to onboard electronic controllers, what is needed to ensure accurate readings, unified operation, of course, easy to use controls while preventing damage from vibration, shock caused by daily repeated use, wear and tear, particularly for eVTOLs using fly-by-wire systems?
Yeah, another good question. And the electric motors are controlled typically by an inverter that's hooked up to a power distribution unit. So the battery is the source of the power, and then it goes into a power distribution unit that will control the types of power being run to different systems, whether they're avionics or the propulsion systems. And today, with the types of power that we're talking, the megawatts of power, we need new types of switching control. And today we're doing this both with traditional electromagnetic controls, but also in the future, we're developing solid state controls. So what that does is that enables better reliability because it doesn't wear out the contact surfaces that are doing the power switching. It can have things like fault detection embedded into the electronic controls. And these are things that I think for the future are required to do things more reliably, safely, and enable electric flight.
We've heard several times in the conversation, kind of like a learning curve because everything is so new and it's rapidly changing and it's exciting, but every day there's more information coming in and you're learning more and more things. So how much have electric aircraft engineers learned over the past, say, 2 years? And then what gaps remain between where they are and where they need to be?
Yeah, another great question. So when we go from prototype to production, or even before that, from concept to prototype to production, we think through how we would build an airplane or aircraft and routing things like these cables. Once they get these in hand and see how difficult it is sometimes to route a heavy power cable, we now have to rethink how we do build things to scale up for production. So what we've learned over the past 2 years is going from just the concept of getting something into air to fly, and then we get the concept of, okay, how do I now scale this up to make potentially hundreds or thousands of airplanes? And the other thing they have been evaluating, again, looking at perhaps automotive grade products and can they be used? And that's the cables, the connectors, the power switching types of products, the sensors, maybe even fiber optics. They can now translate into using some new technology that can help save weight, not just get something off the ground, but to fly efficiently. So when we think about this whole transition, we're learning a lot with what works. We're learning a lot from the aerodynamics perspective and the aerostructures perspective. We also have to consider the whole maintenance philosophy, again, how we do charging and all this. Do you take batteries in and out, or do you hook up to a power cable? So I think there's a lot of things still being learned, and those are some of the gaps. So the infrastructure of how do I do quick charging? Where are those charge access points going to be? And all this still, I think, is being discussed in the electric flight community.
Looking to the future, where do you see things going? What do you see driving market adoption and demand for electric aircraft? And then what could potentially limit this?
Yeah, so it's really interesting here because there's kind of two forcing functions. Firstly is the huge desire for aerospace or aviation to limit carbon dioxide emissions. And there's governments worldwide are looking to use legislation and regulation to ensure aerospace does its part. We recently see the introduction of sustainable aviation fuel, a lot of hydrogen testing with running of gas turbines, for example. Electrified aircraft are a part of that. Whether it's hybrid or fully electric, there's a lot of work going into ensuring that these emissions, whether it's carbon dioxide or NOx or no noise, are reduced. We see a lot of incidents where traffic is being lowered. Example, in Holland, the Schiphol airport is limiting the number of movements for aircraft, particularly business jet. And we see in France where there is an alternative to go by high-speed rail between cities, domestic flights are banned, even if the rail ticket is actually 2 or 3 or even greater times for the paying customer. So we're seeing kind of a lot of legislation happening to reduce that. So that's one area where there's going to be a drive for electric aircraft. And secondly, the big driver for that is kind of offering up this greater mobility option to people. And some of the first incidents of business cases, use cases for eVTOL was getting across town. Sao Paulo is one of the largest cities in the world, and it already has an urban air mobility option through existing helicopters. And the effect of that is you reduce a 2.5-hour commute from the airport into the center of Sao Paulo to something like 20 or 30 minutes. Today, we see helicopters in Manhattan ferrying people a 5-minute flight between JFK and downtown Manhattan which can take an hour typically by road. So that's kind of the very first kind of demand option, where, as already said, that the 3 or 5 time reduction in operating cost for mobile transit through the air is going to be offering high speed, reliable, and safe flight for pretty much everyday people. Then it comes to kind of connecting communities, and once the industry starts showing that there are options for people, certainly in places where the road and rail infrastructure isn't quite there. The UK is one of them, where we can offer up regional transportation. Across Florida, for example, is another use case. Across Norway is another. UK is another. Anything that goes across lakes and rivers, seas. The Caribbean is another one, where it can cost $700 for a 20-minute flight to go between islands. So it does offer up kind of everyday opportunities for people, and that demand isn't there yet because it's kind of seen as not available. But once it starts happening, it'll be a self-generating demand once those kind of options start opening up. But in terms of what the limitations could be, now there have been various studies on this throughout the European Union and other cases where in the US, where eVTOL companies have done their own research. Some of the big worries is noise. How noisy are these aircraft going to be? And there's been some great demonstrations of how quiet these aircraft are. A lot quieter than turboprop general aviation and helicopters. Almost to speaking level as it flies overhead. So very very good to see. Safety is another aspect. Are these aircraft safe to fly? And that's a very key thing. They are aircraft. They are not ground vehicles. They are not electric cars. They're not electric trucks. So they do abide by aviation safety rules, which are incredibly safe. It's the safest form of transport nowadays. Access is kind of interesting here, because it's not just about giving people a way to drive to a vertiport, or how they get their taxi to an airport and then away from an airport to their place of work in the center of town, for example. So it's not just about access there. It's about financial access. How do you make this accessible to perhaps not just a group of elites, but make it accessible to individuals at a lower income level, but also in terms of physical and mental ability as well. So are these aircraft accessible for wheelchair users, or those who have personal space issues? And one of the issues I was kind of brought to my attention was how autonomous vehicles perhaps are not appealing to women users because of the lack of someone in authority in a vehicle. Which I thought was very interesting. So how can we make these aircraft fully accessible for everyone? And of course, kind of going back to the safety and reliability aspect, we've got to make sure these aircraft are robust and demonstrate that to people, that they are safe to use in every way. So safety, reliability, noise, making as these aircraft as little impact as possible to people today, while giving them greater mobility access than they have today. So can we get the both? I think we can. I think we can get both aspects here with careful design work, working with providers like ourselves to look at optimizing components and subsystems to really kind of help, as I said, the evolution of this industry going forward. There's a lot to do, and it's super interesting, and great to be part of it.
One thing that I think would really help to drive market adoption is the whole cargo area, as well as military. And this is an area where they can do a lot of training and get a lot of that required flight time hours in a very low risk environment by moving cargo around with some of these eVTOL type vehicles. Some of the limitations I would see with market adoption are the ride experience. And when people are used to a commercial aircraft ride experience, it's designed to be very, very comfortable. And perhaps riding in an eVTOL might feel like more of a roller coaster ride or something like that. And as an outsider, think about sitting in a cafe in Paris, enjoying your coffee and croissant, and all of a sudden this eVTOL comes down, blows a lot of wind, dirt, and debris everywhere, and people may just have a different feeling about that, and not just that, but in addition to those factors, but also privacy. So if you have access now vertically into different spaces, maybe your own backyard, and maybe your neighbor is flying his eVTOL, maybe you want some privacy that is now intruded upon with this type of aircraft. So these are just some of the other aspects that could be considered with market adoption.
Yeah, you make a good point, Matt, because I fly small four-seater general aviation aircraft, and you can get quite a ride in those on the crosswinds, especially when you come into land. So yeah, that's another part of it is how comfortable you're going to be in this very, very stiff airframe vehicles. You're going to get a lot of turbulence around skyscrapers, etc. if you're not careful. So yeah, that ride quality important.
We covered a lot of territory, literally and figuratively, today, talking about, of course, the evolution of eVTOL technologies. And I want to thank both of my guests, Matt Macalonis, an engineering fellow of TE Connectivity and is the director of advanced systems and architecture for the aerospace and defense business unit. And Martin Cullen is a senior business development manager at TE Connectivity, serving as the global eVTOL leader for the aerospace business. Thank you both, gentlemen, for being with me today. I'm sure people want more information. They may have more questions. Is there any place you can send them? Where can they reach out?
Sure. So I'd be happy to speak to anyone who wants to be more involved with TE, how we can help them design their components. So best to reach me on my work email, which is just my name. It's martin.cullen@te.com. It'd be great to hear from you.
So if anyone would like to reach out to me, you can reach me on LinkedIn under my name, Matt Macalonis at TE Connectivity, or my email is mmacaloni@te.com.
Thank you both for joining me today. Great conversation. And of course, you can go to te.com for more information there. Want to thank you for listening to the Our Connected World podcast today, talking about the evolution of eVTOL technologies. And once again, a reminder, this is part one. We have a two-parter for this because there's just so much great information to get to. So be sure to subscribe to the Our Connected World podcast so you can hear more great conversations, and definitely part two of this one. I'm your host, Michelle Dawn Mooney, and we hope to connect with you again soon.